Hello everyone. Today we are going to discuss on chapter 3, current flow in homogeneous semiconductor, focusing on diffusion current. Before I start, let me recap on what we have learned previously. Previously, we have learned that there are two types of main mechanism of current flow in semiconductor. One is drift current and another is diffusion current. I hope you still remember what is drift current. Drift current is the current that results from the motion of electrons and holes in the presence of electric field. And another mechanism of current flow is diffusion current, which is what we are going to learn today. So, at this end of this video, I hope you will be able to explain the mechanism of diffusion current flow in a semiconductor. Diffusion is the process of particles moving from high concentration area to low concentration area. In real-life example, you can imagine pouring a very thick sugar water or syrup into a glass of water. You can see that the syrup diffuses into the plain water. That is exactly what happens in a semiconductor that has non-uniform carrier concentration. Take this bar for example. Here is the region with higher carrier concentration. In this case, these are electrons, and this is the region of lower electron concentration. This phenomena can be represented in a graph as shown here in figure B. In figure B, y-axis shows the carrier concentration and x-axis shows the position. So, in this case, the electrons will move from left region of higher concentration to the right region of low concentration. Thus, this will result in diffusion current. Let's discuss further. As we have seen in figure A on the previous slide, in this case, since there is no electric field, the electrons will move from this left region of higher concentration to the right region of lower concentration. Thus, this will result in diffusion current. Since in this example, the moving particles are electrons, thus the electron diffusion current will have a direction that is opposite to the electron movement, in this case, from right to left. At the same time, the holes will move from high concentration region to low concentration region. In this case, the region having high holes concentration is on the right. Thus, holes will move from high concentration region on the right to the lower concentration region on the left. This also will result in diffusion current. Since the moving particles are holes, thus the holes diffusion current will be moving in the same direction with holes. In this example, the hole diffusion current will move from right to left. Since the direction of electrons' diffusion current is the same with holes' diffusion current, a total of diffusion current density from right to left is generated. For the calculation, the diffusion current density is given with these equations. The main factors that determine the current density are dN and dP, which are the diffusion coefficients for electrons and holes, and also the changes of electrons and holes concentration with regards to position, given by dnx dx or dpx dx. The diffusion coefficients are given by this graph. You can find this graph in your textbook, and there is a relation between d and mu as can be seen here in the Einstein relation. Mu is the mobility as what we have learned in chapter 3 for drift current. I hope you still remember on how to read this graph. The method is the same as reading the graph of mobility that we have learned during the drift current topic. You will have to determine the majority and minority carriers of the material and read the lines accordingly. So, the example that we have discussed just now is without the electric field. If the same material is put under electric field, thus both diffusion and drift currents will appear. The total current density then can be calculated using both equations combined as shown here. And with Einstein relation, the equations can be further simplified as shown here. Then, combining the equations in the previous slide, we have the equation for the total current density. The total current density equation has four things that need to be considered. We have the electron drift current density, Jn drift, hole drift current density, Jp drift, electron diffusion current density, Jn diff, and hole diffusion current density, Jp diff. Please take note on this negative sign for hole diffusion current density. Note that the drift current factors have the electric field and mobilities, and the diffusion current factors have the diffusion coefficient and also the differentiation of electrons and holes concentrations in them. So, that's all for this subtopic. I hope you managed to understand. Please communicate with me for any questions and discussions via WhatsApp or at the comment section of this video post at our FB page. Thank you.